Hello, YouTube! Today we're going to be talking about hills, and specifically we're going to be talking about ways that you can take problems with hills and make them much, much easier. So that's the goal. It is going to be a little bit weird, in particular, again, just focusing on how to model stuff happening on a hill. And the big one is being able to rotate the way you're thinking about the problem so that instead of thinking the hill as a diagonal, you're thinking of it as a horizontal thing, and then it's just the forces happen to go in really weird directions. Because that makes the math much, much easier. So we're just going to kind of hop into it and do an example problem. And that'll be it. So, and then take our takeaways and actually put that in a review slide, actually. So, not quite it. Okay, so our info for this problem is that we've got a box on a hill. We know that that hill is at a 37-degree angle. It's a 3 kilogram box. We know that the kinetic coefficient of friction is 0.2. We know that it's moving at a velocity of 10 meters per second down the hill, and we know that we're pulling it at a, wow, I really went all out on this one, 30-degree angle with a force of tension, which is 20 newtons. For A, we are asked to find the acceleration. For B, we were asked to find the acceleration if V is up the hill instead of down the hill. So, I suppose let's just get to it then. So in particular, looking at this one, if we do our free body diagram as is, and we start the setup that we've been using so far, and I will actually label this specifically as the old way. We'll have our hill going like this as a dotted line. This isn't a force. I just want to make sure that I'm keeping track of it. We'll have gravity going down, so that part's nice and easy. We'll have this force of tension going at a 37-degree angle from the horizontal plus a 30-degree angle from that. So it's a total of a 67-degree angle from the horizontal. Our normal force is at a 90-degree angle from the hill, which means it's at a 53-degree angle from the horizontal. So that's Fn. And our friction is going to be going down the hill, which means that our friction is at opposite interior angles. So this is a 37-degree angle from the horizontal. The big problem here is that our variables in all of this are going to be the acceleration, which we don't know, and there's going to be an acceleration in the x direction, but because it's going to be accelerating in either this direction or this direction, depending on whether or not friction or tension is bigger, there's going to be some component of the acceleration in the x direction, and there's going to be some component of the acceleration in the y direction. And our equations for this are going to look something like ftx, which we're going to have to use trig to get, plus for the x direction, ftx minus fnx minus ffx, and that's all going to equal max. And in the y direction, we'll have mg going down, so minus mg from this one. For this component, we'll get a normal force in the y direction going up, and for tension, we'll get a normal force in the y direction going up, and for friction, we'll get a force of friction in the y direction going down, and all of that will equal may. And then additionally, because there's friction equation with a coefficient of friction, we'll have that our force of kinetic friction is equal to mu k times Fn. So we'll have this system of equations with three variables, a whole lot of trig, and every single one of these equations, except maybe ff equals mu k fn, is going to be honestly just brutal. I don't really want to do that. So it would be really great if there was a shortcut that made these equations a lot easier. And thankfully there is. So again, if you want to do it this way, you certainly can, but there is a slightly easier way. And that's to take your sheet of paper and rotate it. Because the weird thing about components is as long as they're perpendicular to each other, it still works. You don't actually have to be any more careful than that. So once I do that rotation, if I make it so that my hill is horizontal, what that'll look like when I redraw it is that in red, I've got, actually I should be careful with that for colorblind. In a dotted line, I've got my hill. Friction goes down the hill. So this is nice because this won't have components. This is just going straight sideways. My normal force, let's see if I can get the camera a little bit better. My normal force goes just perpendicular to hill. Also nice because it doesn't have any weird components. My tension is going to have some components, but it's actually not too out of the usual for what we're used to. The only thing that's different about this one is, I guess the reason it's not particularly out of the normal is because we know its angle from the hill. So I don't have to do that whole thing with the 67 degrees where I'm like adding up multiple angles. The only one that's going to be really weird here is gravity. Because gravity goes straight down, but I've rotated my head so that what looks like it's down to me isn't straight down anymore. So gravity is actually going to go this way. And I do kind of want to be somewhat careful about the angle. So this is 37, this is 37, these two are perpendicular, this is 53. So from here to here is 53, so it's going to be a bit bigger than 45, so something like this. And that's mg. Again, we are going to have to be a little bit careful about the geometry. If I want the angle between gravity and the hill, looking at this, we've got that from here to here is 180, or I could say that from here to here is 90. And what's a nicer way to do this? All right, so the way that I tend to do it is basically actually using the hill angle itself. If we look at this, this is with what the ground would be if it's not a hill, that's 37 degrees. I can make a triangle with that and gravity that'll make a right triangle. So this will be 53 degrees. Because this is 53 degrees, if I make my components here, with my x going along the hill, and my y going away from the hill, or sorry, perpendicular to the hill, then this angle right here is 37 degrees, or the hill angle. So in particular, what we've done is broken that up so that it's based on the hill angle and which way is going along the hill or parallel to the hill, and which way is going into or out of the hill or perpendicular to the hill. And so when I'm labeling stuff, I'm actually going to label this one as the force of gravity that's perpendicular. So that's why I've got that little perpendicular symbol to the hill. And that one is adjacent to my hill angle. So that is mg times the cosine of theta. Up here, we'll have the force of gravity that's parallel to the hill. And that'll be mg times the sine of theta. And theta is my hill angle. So in this case, mg cosine theta will be 3 times 10 times the cosine of 37, which is 30 cosine 37. which is 24. And this one will be 30 times the sine of 37, which is 18. So I have my components for gravity. If I do the same setup for tension, we'll have Ft cosine 30. So 20 times the cosine of 30, which is not going to be particularly close to a whole number. Oops. I guess I could have just multiplied by 10, but that's fine. Which is 17, we'll call it 17. And then my y component, which is Ft sine 30, which should just be 10. Great. And so what's nice about this in particular is that our object is not going into the hill, nor is our object going out of the hill. It's staying on the hill. So it's not moving perpendicular to the hill, and it stays not moving perpendicular to the hill. And those two things in combination mean that my acceleration that's perpendicular to the hill, oops, I did t instead of perpendicular, is actually 0 for this one. And that's the big thing that makes this a lot easier, because it also means that my net force perpendicular, I keep doing that, net force perpendicular to the hill will also need to be 0. And so if I'm doing the perpendicular direction and I'm taking what it look for this, once I've rotated, it looks like just y. That'll be Fn plus Fty minus mg times the cosine, I have to be careful about that, of theta for just the perpendicular part. And that needs to equal 0. And this makes my algebra way nicer because one of my things equals 0. Setting it up for the parallel part, we've got that there's some part of tension going forward. 2 lines means parallel. There's some, and then there's friction, which in this case is going against it. And my parallel acceleration is the only acceleration that there is. If I'm looking at this, this isn't actually too bad, because I know this. I still need the force of friction. I still need the acceleration. It's what I'm looking for, but I know the mass. And so I need to figure out a way to figure out how big friction is. Or at least how big friction is in terms of the acceleration, although for this one we can just get the friction. So what we can do for that is start looking at our friction equation. Our force of kinetic friction is going to be equal to mu k, which we know, times the normal force. Looking at this, we know mu k, we want the force of kinetic friction, we need the normal force to get it. So we start looking for equations with normal force. Well, the perpendicular equation has normal force. We know the force of tension in the y direction, we know m, we know g, we know the theta for this one. So we can find our normal force using this perpendicular. So we're going to have 3 equations kind of daisy-chained together. We'll use the first one to get our normal force. We'll use the equation for friction to get our friction. And then we'll use our equation for the parallel motion, the motion up and down the hill, to figure out how much it's accelerating up and down the hill. So labeling out our steps for this one, we've pretty much got step 1, make the old free body diagram. Step 2, make the new rotated free body diagram. Step 3 would be set up equations. And don't forget friction if there's friction in the problem. And then step 4 is going to be solve out for the things you're actually looking for. So to solve it all out, we're first going to start with the normal force because we figured out that we need that in order to get the friction. Well, again, our only variable here is normal force. So it's just some pretty, hopefully straightforward algebra where we want to get rid of FTY and mg cosine theta. So minus FTY plus mg cosine theta minus FTY plus mg cosine theta. If you want to leave it all as variables, which you should probably get in the habit of doing, it'll look like this. And that'll be equal to, if we're plugging in our values, 30 times, actually I already did this, so 24 minus 10. So 14 is our normal force. So at this point we know our normal force. Now that's not our answer, but it's this next step in our answer, because we can take that and we can plug it into the equation where force of kinetic friction is equal to mu k times Fn, which in this case is going to be, with the variables, mu k times mg cosine theta minus fty, or with the numbers, mu is 0.2, so 0.2 times 14, which is 2.8. From there, we can take that and plug it in up here, and all we have to do is divide by mass and we're done. So taking that and bringing it over, and unfortunately I'm going to have to flip the sheet because I'm very out of space. We've got Fk equals mu k times mg cosine theta minus fty, which was 2.8, and that is getting plugged into ftx minus force of friction kinetic equals mass times the parallel acceleration. And because we are looking for the parallel acceleration, I'm actually going to divide by the mass before I plug anything in, just to make my life a little easier and have to write a bit less. And that'll give me ftx, oops, this should be parallel. ft parallel, this should actually be ft perpendicular, minus the force of kinetic friction divided by m is equal to the acceleration. But if I take this and I plug it in, what we'll get is the old equation that we had before with ft parallel minus this stuff in parentheses, mu k mg cosine theta minus ft perpendicular, all of which is divided by the mass. And that'll equal this one, which I think was 17, but let's double check the sheet. Yep, 17. Minus 2.8 divided by 3, I think. So parentheses for the numerator, 17 minus 2.8, close the parentheses and divide by the denominator of 3. And that'll give us 4.7, which is our acceleration. And this is positive, which means it's going up the hill. So this thing is slowing down. Because the person is pulling it up the hill more than gravity and friction are pulling it down the hill combined, basically. Oh. Poo. I messed this up, actually. One sec. When I was doing my parallel stuff, I forgot that if you look over here, there's this blue component for gravity. This should actually include minus mg sine theta. So over here, this should also be minus mg sine theta. This should also be minus mg sine theta. This should also be minus mg sine theta. Mg sine theta was 18. So this is actually going to be accelerating down the hill. Oops, oops, oops. Minus. Did I put my friction backwards? I put my friction backwards. I'm all over the place today. All right, so the object is sliding down the hill, which means that friction needs to go up the hill. Sorry if you saw that at the beginning and have just been internally screaming the entire time. This will be what happens for part B. The force of friction should be going up the hill. Because the force of friction should be going up the hill, this one in, and that should be true here as well. All of the directionals should be backwards. It should be in the positive x direction and the positive y direction. And coming over here, it should be going up the hill. So that should be positive. That should be positive. That should be positive. That should be positive. Something about a teachable moment where mistakes happen, and as long as you're being careful throughout the way, and this is part of why it's so important to show your work, and like you can recover pretty quickly as long as you are careful about it and know what's up. But mostly just, whoops! All right, so I am going to have to say, because this one's minus 18, do this again. So let's do 17 minus 2.8. And this is part of the reason why I like writing out the variables, by the way, is because if I had just been writing out the numbers the whole time and combining them as I went, it would be a lot more difficult to go back. And this should be plus 2.8. It would be a lot more difficult to go back and fix it if I made a mistake anywhere along the way. All right, so our acceleration is positive 0.6, which does again mean that the acceleration is going up the hill. Friction combined with the person pulling it up the hill is enough to make it try to accelerate up the hill, which, because it's moving down the hill, means that it's slowing down. For B, our problems are going to be basically the exact same. We haven't changed our tension, we haven't changed our gravity, and those were the two things that mattered for normal force. So because we haven't changed our normal force, we haven't changed the size of our friction. The only thing that will change is pretty much just that the problem I had done a second ago, where friction was going down the hill because it's moving up the hill, is now the case. And so when we draw our rotated free body diagram, we'll have gravity going down the hill. We'll have the two components of gravity again. And this is one of the few things that I'll tell you to memorize, because honestly, redoing the algebra, the geometry every time is a huge pain, for me anyway. Mg cosine theta is the one that's perpendicular. Mg sine theta. So the part of gravity that smushes it into the hill is mg cosine theta, where theta is the hill angle between the hill and the ground. The part of gravity that smushes it down the hill is mg sine theta. And in particular, I want you to remember that because that is flipped from what people are normally used to, because this is basically like the y is cosine, the x is sine. It certainly happens, and it especially happens here. We've got our ft going up the hill. Where we've got ft times the cosine of, sine of 30, and this one was ft times the cosine of 30. And then we've got our friction, this time going down the hill. And friction's actually a lot smaller than gravity, so I'm not going to make it bigger. And so that's our force of kinetic friction. And then going perpendicular to the hill, we still have our normal force. So the only difference here is that because friction is now going down the hill like I had drawn it originally, instead of going up the hill like I should have drawn it last time, when we set up our equation in the parallel direction, the direction that's going up and down the hill, we'll have ft cosine 30, same as it was before, but positive. we'll have gravity, same as it was before, and negative. But we'll have friction this time also being negative. And so our algebra is going to work out the same way in every part of this. It's just that when we get to the end, at this point, we'll have a minus sign here like I'd originally had last time instead of a plus sign. So we'll have plus ft parallel minus mu k mg cosine theta minus ft perpendicular minus mg sine theta, all of that divided by m. And so when I plug in my numbers, it'll be 17 minus 2.8 instead of plus 2.8 minus 18 divided by 3, and that'll be, just go ahead and swap in the minus. Another reason I like putting everything in the calculator in one step. Oops. Which is negative 1.3. So this time, when it's going up the hill, because friction is working together with gravity, the acceleration is again going to be down the hill, and it will, that's not on the screen, will be going down the hill, and the object will wind up slowing down once again. So pretty much what this is telling us between these two answers is that no matter which way this object is trying to move on this hill, as long as it's moving, it'll be slowing down until eventually it stops, at which point friction should be enough to make it stick. So, what were the big takeaways? Be careful when you're trying the direction of friction. Don't forget any of your forces. Those are two of the first big takeaways from the mistakes that I made. But in particular, what you're going to be doing is taking your reference frame, and instead of thinking of x and y as being vertical and horizontal, you can just tilt your head. And when you do that, you'll be thinking of your x and y so that your x goes the same way as the hill, and your y goes perpendicular to the hill. What this does is that it makes it so that normal force is always just perpendicular. Great. So your normal force will always be a perpendicular. Your gravity will be such that the perpendicular part of gravity will be mg times the cosine of theta, and your parallel part of gravity will be mg times the sine of theta, and friction will always be along the hill, which means that it's parallel. Because the object is staying on the hill, the big reason we did this is to make it so that we don't have acceleration in multiple directions, because that makes the algebra really messy. And instead, we can just say that our acceleration in the new y direction is going to be 0 because it's staying on the hill. And those are sort of the big takeaways for when you're setting this stuff up. You can combine that with friction. When we learn about systems next, you can combine that with systems. Basically, all three of the things that we learned sort of post everything can be combined with each other, which is a little unfortunate because it is very tricky, but that's it. All right, so that's how you deal with hills. Thanks for watching, and goodbye, YouTube.